Hello! Today we're going to look at one of the main quantities that describes the heating of various substances. This quantity is called thermal capacity. What is it? And in general, what is heat? What is the amount of heat in the framework of the phenomenon under study? This question has been of interest for quite a long time. Scientists have always tried to connect it with some mechanical processes, that is to say, to show that, in general, the law of conservation of energy is quite universal in terms of transferring energy from one body to another or transforming it from one form to another. And so, in particular, the famous scientist James Joule was just studying this question, and he did various experiments and he proved for the first time that, in fact, the amount of energy remains the same. It can only change its form, and not only in mechanics, but also in the context of other related sections, for example, mechanics and heat. That is, we can say that energy can change from mechanical to thermal form and vice versa. To do this, we just need to build a certain device that can do this. And in particular, such a device has been built, if you can show how it works schematically. It was a so-called insulated vessel. So it was important to keep the insulated system inside the water that was poured inside this vessel. That is, the walls of this vessel, they didn't allow heat to pass through. You and I know that there are various devices of this type. The most famous one is probably the TAMOS. It's got a vacuum inside of it. Between the two walls, there's a vacuumed space that doesn't let the heat out, and so inside the hot tea poured in can be kept hot for quite a long time. And this system was set up in such a way that inside there was a spinner with blades mounted on a movable rotating axis. And so this spinner could be spun around by a number of weights that were hanging from both sides. So the weights, as they came down, would spin the system. And by friction against the water started to heat up. Naturally, in this case, it had to be fixed here with a thermometer. And measure the temperature of this liquid and keep an eye on it. And it turned out that the amount of potential energy lost, which the scientists recorded when observing this process, was almost as much as the amount of energy being gained, the energy of the liquid itself. That is, these amounts of energy were equivalent to each other. So the change in potential energy for the mechanical system was essentially the same as the change of the internal energy of this liquid. So the heating was due to the fact that it was energy. Energy was transferred from one kind of energy to another. Therefore, in this case, we can say that here there is a heating of the liquid due to the accomplishment of mechanical work. And this is a form of changing the internal energy of an object. That is, to do work on it. Another form of energy change, as you and I know, is the transfer of heat. That is, we could heat water, for example, just by putting it on some fire. And in this way, we would also get water heating due to the heat transfer process. So this is one of the basic laws of thermodynamics, when we get the ability to change the internal energy of different objects. In two ways. Once again, the first way is heat transfer. The second way is by doing mechanical work. So it was necessary in order to introduce a certain quantity, which is exactly how much energy a given body has gained by changing its temperature. Or conversely, how much energy it gave up in the process of changing its temperature. Accordingly, this quantity is called directly the amount of heat, and it gets its name from the fact that there is some amount of energy, heat energy, which is transferred from one object to another, and is denoted by the big letter Q. And of course, since we're talking about energy, the unit of measurement for this parameter will also be J. So in this case, we're going to be recording the word heat, exactly the amount of heat that the body loses or conversely gains. Now the question is how to calculate this amount of heat. From the point of view of calculation of mechanical work, we can understand that it will be, let's say, a change of potential energy. But how do we calculate the amount of heat when we just have a heat transfer process going on, for example? So we put two objects together at different temperatures, and some amount of heat has transferred from one object to the other. But the question is how to calculate now this amount of heat, what it depends on. And here a very important circumstance is that, first of all, the amount of heat. That, let's say, the same water when it's heated, will of course depend directly on how many degrees we're going to heat that water. So the greater the change in temperature of a given body, the correspondingly greater the amount of heat it will receive. Further, it is natural to assume that the amount of heat depends on the mass of the object. That is, the more matter there is in the object, so the more molecules you have to accelerate in this heating, the more energy you need. So in this case, there's a direct correlation with the mass of the substance. We can look at different situations where we've got two different substances. Let's say we have a steel bar of a certain mass. So let's say it's a bar made out of steel and the same bar made out of aluminum. We remember that aluminum is less dense than steel, and for a given mass, the same mass, it will have a greater volume. But it turns out, if we want to heat these substances to the same dT, so we're going to heat them by a certain number of degrees, the amount of energy required to heat these different substances will be different. So here it turns out we will spend, let's say, the amount of heat Q1, and here this amount of heat will be different. It is clear that it is connected with the internal structure of these objects, i.e., they absorb this heat differently. So we need different amounts of energy to heat the same amount of degrees. Therefore, in order to describe this dependence of this parameter on the substance on its species, it is necessary to introduce some coefficient that will characterize the substance itself. That is, what we are heating. And in this case, one more parameter is introduced, which is already a certain constant for certain substances and has its certain tabular values for different substances with which we will work with you. This thing is called specific heat capacity. Specific heat capacity is denoted by the small letter c, and it will show how much heat it would take to heat 1 kilogram of a given substance by one degree. That is directly the ratio of that amount of heat to the mass of the object and the change in temperature by 1 degree, either Celsius or Kelvin. Here, by the way, it doesn't matter what units you work in because as we remember, the degree world of these scales is the same, and so the difference in temperature in Celsius or Kelvin will be the same. So here you can write in either Celsius or Kelvin scale these parameters. So the unit of measurement for this quantity will be defined as joules per kilogram, and let's say Kelvin. Thus, in order to calculate the amount of heat that is needed to heat or cool any object, we already have the final formula that we're going to use with you to solve problems. All the necessary factors to make this calculation are taken into account here. So there's a dependence on the substance, there's its quantity, and an understanding of how many degrees, let's say, we want to heat this object. Another very important law that we should mention is the law of balance. That is, when there is a heat exchange between different objects, we have to realize that some heat is lost by the hotter object and some heat is gained by the colder object. The colder object gains. In this case, this balance will be a consequence of the law of conservation of energy. And that's the form of the law that we're going to use in the future, which is the total energy change of the system is equal to zero. It means that some object has gained energy and some object has lost energy. And in the form of these quantities of heat and all the processes that occur in this phenomenon, we will prescribe each process by its own formula. Of course, we don't just have heating or cooling processes in nature. There are many others that we'll talk about in our next lessons. In our next few lessons, but this balance equation will work, no matter how many processes have occurred or what processes have occurred. So this is the end of our lesson. See you in our next lessons. Goodbye, everyone.